chapter 18. There's a bunch of stuff in this chapter, so I'm just giving a summary, and I'm not going to do it all justice. There's a whole bunch of cool stuff, but let me start with one of the things that we looked at before that we're going to kind of need, and that's this relationship between electric fields, charges, and a change in electric potential. So remember that if I have positive charges, they make an electric field that points away. Negative charges make an electric field that points towards them. And also the electric field is the force per unit charge. We'll actually get into that too. If I have an arrangement like this with a parallel plate and another parallel plate, then I get a constant electric field. And in a constant electric field, if I move from one point to another in the direction of the electric field, I get a change in potential. And this is only true for constant E, and in the direction. Okay, so it's not always true. This is a specialized case. But then I get a drop in electric potential depending on the value of the electric field E and how far you moved. This is also going to be useful later. We define the capacitance as the ratio of charge to the change in potential on these parallel plates, and also the electric field inside there depends on the charge and the size. So really the charge per unit area. Okay, so now let me get back to my page right here to make sure I cover all of the important concepts. Let's review real quickly what happens if I have a cylinder, a metal cylinder. If I have a metal cylinder, what makes metals different is that we can model this as having a bunch of positive atomic cores, we'll call those, and they all have at least one free electron. That's what makes metals nice. And so this electron doesn't really matter who it pairs up with, it can move around. And so if I apply an electric field in here, then the cores aren't going to move, they're fixed. But that negative electron, if I apply an electric field going that way, then this is going to feel a force that way, F. And if there's a force on an object, it's going to accelerate. So these negative charges, by applying this electric field inside, are going to accelerate this way. Now, in a normal wire, those negative charges would build up here, that'd leave positives over here, and we'd get a net electric field of 0 inside. But if it's connected to a circuit, we can actually get a constant flow of charge. Now, there is something to consider. If I have these charges in here, and I look at the velocity as a function of time, it's going to speed up. But at some point, it's going to interact with the rest of the material, and it will stop. And then it's going to speed up again, but maybe it doesn't get as far, and then it's going to speed up again, and then it's going to speed up again, like that. So it's going to keep speeding up and stopping. And over we can average this as what we call the drift velocity. But the most important thing is that if I count the number of charges that move past this point per second, we call that the electric current. So current is defined I as delta Q, change in current, over the change in time. And this has units of coulombs, the unit for charge, and per second. And a coulomb per second is an amp, or an ampere, ampere, but we always call it amp. Okay, so that's the definition of electric current. If I have negative charges moving this way, or positive charges moving that way, in this definition, you don't see a difference. They look the same. Okay, so it doesn't really matter which way I could have negatives moving this way or positives moving that way. When we show the direction of current, it's the direction a positive charge would be moving if that is what is moving. Although in most cases, it's the negative charges that move because of the nature of metals. Not always, but in most cases. Now, this there is a relationship between the drift velocity, which is not very high, right? The drift velocity for a charge moving in a wire doesn't necessarily have to be high. But if I have a whole bunch of charges or a large area, then I can get that high. But in general, we can write the current in terms of the drift velocity as N, how did they do it? E, A, V, D. So that's the drift velocity, which actually depends on, I'm going to put this, depends on E, the electric field, and the material. So it doesn't show you everything, but if I do increase electric field, these are going to increase at a higher acceleration. A is the cross-sectional area. Right, so that's this thing over here. How wide is the wire? E is the charge carrier. So for most cases, this would be an electron. So this would be equal to 1.6 times 10 to the negative 19th coulombs. And then N is the charge carrier density. Let's put that as just charge density. It's how many charges per unit volume you have. You have, and depends on the material. So that depends on the material. That depends on the material. This depends on the wire, right? Because if I make the wire bigger and I keep everything else the same, I'm going to have a higher current. And that depends on the wire plus the electric field. Okay, but the electric current is the flow of charge. That's the important thing. Now, we can actually also group some of these things together because the drift velocity depends on the electric field, but the electric field depends on something that we can more easily measure, which is the change in potential. So with that, we get the definition of resistance. There's really two ways to look at these. We can look at this at an atomic level. We can consider the electric fields and the moving charges, or we can look at the macroscopic properties and we'll use resistance. And we define resistance as the change in voltage divided by the current. So if I take a wire and I measure delta V and I measure the current I, the ratio of those will tell me something about that wire. If I have a lower resistance wire for the same delta V, I'm going to get a much higher current. And it's not always a constant. Not always constant. It can be, or very approximately. If it is constant, we call that an ohmic material because we measure these resistance in if delta V over I would be units of volts per amp, and that's equal to an ohm. And we also write that as the capital omega for ohms. I don't know why, but we do. If this, let me also say, this resistance depends on the material of the wire or element and the physical dimensions. We can actually separate that out. We can actually say the resistance is some resistivity times the length divided by the area. So where the Greek letter rho is resistivity in units of ohms per meter. So this just depends on the type of material, and L and A are the length and cross-sectional area of the material. And the nice thing about this is that we can just look at interactions or phenomena where the material changes or the properties of the material changes. One of the most common ones is change in temperature. And so we can actually write this, rho equals rho times rho 0 times 1 plus alpha delta T. This is the change in resistivity as a function of temperature. So if I know some set resistivity at some, say, room temperature, and then the change in temperature with respect to that temperature, delta T, and alpha is a parameter about the material, then I can find the new material. And this says something really important. As things get hot, as delta T is large, it increases the resistivity. So it'll increase the resistance of the wire too. And the same thing is true. If you decrease the temperature, you decrease the resistance. Okay. Now we can get to one other version of this is called Ohm's law. This says that if I have some wire, I'll just put it, special wires connecting my wire, and I measure the current coming in, and I measure the delta V, then I can write this delta V as IR. So the change in voltage going from this side to that side is the current passing through it times the resistance. Now, if the current's going this way, this side's going to be plus and that side's going to be minus. So if I go in the same direction as the electric current, delta V is actually going to be negative, right? We always write it like this because it depends on the direction you're looking. If I'm going across this way against the current, I'm going to go from negative to positive, so I'm going to have a positive change in voltage. That's really important for the next two things. But let's look at they do have one thing about batteries. I do have a battery right here. I actually have two. Let's see. That's a D-cell battery with a magnet stuck on it. So one of the important things about batteries is that if this is a 1.5 volt battery, and then I take, let's say, a paper clip with a very low resistance, let's say this has a 1 ohm resistance, which it might be somewhere around there, and I connect one end to the other, then I'm going to get, I could get 1.5 amps of current, but I don't actually get that because we can model a battery as this. There's my actual battery. I can write that as an actual internal battery that looks like this and a resistance. And I've jumped ahead of myself because I haven't shown you these or these. That's a way we represent resistors, and that's the way we represent batteries. And you're saying, well, a battery inside of a battery. Yeah, but this is one way to represent a real battery, because now I can say if there is some internal resistance, they use R, and then I have the internal voltage, we'll call E for electromotive force, then the voltage across this would be voltage of the battery. They write that as delta V. I'll put a B. It's going to be EMF minus IR. So this says that the voltage you actually get out of the battery decreases as the current increases coming out because of that internal resistance. So smaller batteries, a AAA battery is going to have a larger internal resistance, so you can't get as much current out of it. Okay. Now let's look at the simplest circuit in the world. I'm actually going to build a circuit for you. And then I'm going to draw it. And then I'm going to show you the loop and junction rule. So here I actually have two batteries connected together. So this is just one battery and another one, but it allows me to make things work a little bit better. And then I'm just using these bare copper wires just because it looks a little bit better. And so if I take a light bulb and I make this like my resistor, then I'm going to connect this to here. Let's use a little clippy. And then when I connect these two wires, we can see what happens to the bulb. And it does turn on. It's not as bright as I would think. Oh, that's why. It's on. Okay, so it lights up. So I have the very basic circuit. Let's draw this circuit as a circuit diagram, and then I'll explain what's going on. So here I have a battery. And then there I have a resistor. So in this case, the light bulb acts as a resistor. It's really just a super tiny filament in there, a super tiny wire. And this current goes through the bottom, through that little wire, and then back down. And it has current going through it such that it just gets hot. It gets so hot that it glows. So here's my battery. I'll call that E for EMF. Here's my resistor, R, and for a battery, we draw the long side as positive and the short side as negative, so I'll have a current right there. Now, let's get to the most important thing, the loop rule. There are two rules to look at with circuits. The loop rule is essentially this, delta V equals 0. If you remember back from the previous semester of physics, when we looked at potential energy, we could make a potential energy if it was path independent. And when something's path independent, that means that if I start and end at the same location, I have zero change of potential. So that's what this says, right? Because this says if I start here and I go around the loop, then I should get back to where I start, and so I should have a change in potential, which is potential energy per charge, of 0. So let's go this way around the loop. So if I go this way around the loop, then I'm going to cross this battery. And that battery has a change in potential of EMF. Now these other wires are just special magic. They're just perfect wires. But now I'm going to go across here, and I'm going in the direction of the current, And so I'm going to get a voltage drop of minus IR from Ohm's law, and those two have to add up to 0. So that's my very basic circuit equation for a very basic circuit. And we can make more complicated circuits, but that's your very basic one, the loop rule. Now let's look at two resistors in the circuit, and I'm going to call this, I'm going to draw it out, and then I'll actually make it, even though it may not work out too well. So this is what we call resistors in series, R1, R2, and there's my battery, which is larger than it needs to be. So in a resistors in series case, I have the current coming out of the battery, and the current comes through this resistor, and then it all has to go through the next resistor. So they have the same current. So in series, you got to spell it right, same current. So the current through those two is the same. And if I draw this, I'm not going to build it because I don't think it's going to work out well enough. If I do the loop rule in this case, I'm going to start from here, go through that. I get E minus I times R1 minus I times R2 equals 0. And if you factor out the I get E minus I times R1 plus R2 equals 0. And if I do that, then I could just replace these two resistors with one equivalent resistance of R1 plus R2. And so when you have resistors in series, you can replace them with just one single resistor that's equal to the sum of them. And actually, if you had 10 resistors, you could do the same thing. Okay, now let's look at resistors in parallel. We'll make this circuit. So in parallel, I'm going to make the circuit. Hopefully it works out. They have the same change in potential. So here's my circuit. Here's my battery. Let's see if we can make this work. And I'm going to hook up this. Let's just take that wire off. I don't need that one. I'm going to hook this up. Just this one. And I have to have two batteries here because otherwise it won't be bright enough. And in fact, it may still not be bright enough. But okay, you can see that's on. I hope you can see that's on. There. It's on. On. Off. See? Now I'm going to take another bulb and hook it up also. Not in the same way. I'm going to hook it up like this. This is what would be called parallel. Because now if I do the potential from this end to that end, doesn't matter which path I take, it has to be the same change in potential. So they have to have the same change in potential. Let's see if I can get these both on. That one. There. They're both on. They are both on. Trust me. See? Block the light. They're both on. And the nice thing about this is that since they have the same voltage, but they don't have the same current, if I unscrew one of these, the other one stays on. See that one? And that's not true for electric series because in series, that's very bright right there. In electric series, since they have the same current, if I unplug one, they both have 0 current. Okay. So let's do this circuit because it does show us something important. I'm going to draw it. Here's my battery. I'll draw it like this. You could draw it more than one way. So here's EMF. Here's R1. Here's R2, and let's call this I. So the current I comes out here, but at this point, some of the current's going to go this way, and we'll call that I1, and some's going to go that way, I2. And that gives us the next rule, the junction rule. This basically just says that you can't destroy those charges. If I have charges coming into that junction, I have to have the same amount of charges going out. So I in equals I out. So in this case, I would be equal to I1 plus I2. If I use that along with delta V1 equals delta V2, the change in potential across these two, I can combine these two together and replace those two resistors with one equivalent. I'm not going to derive this one. It takes a little bit longer. R equivalent is 1 over R1 plus 1 over R2. Okay. Oh, I didn't mean to, that's still on. Okay, next major important thing. And again, this is a lot of stuff. So really have two important things here. And this one I love a lot. Remember, we talk about power. Power as the rate of change of energy with respect to time. And that's not the electric field, that's energy. So let's put delta energy, delta T. And so if I have energy in units of joules and time in seconds, this is a watt. Well, it turns out that if I have electric current passing through an element, it will also dissipate energy at a rate that we can calculate the power as I delta V. So again, if I is in amps and delta V is in volts, then I get the power in watts. A lot of times you will actually see the energy of a battery as energy times delta T times power. And so if power is in amps times volts, a lot of times you'll see energy delta E for a battery as in amp hours. Right, so if I take, now it doesn't tell you everything, you need to know the voltage. If you take this, multiply it by the voltage, convert hours to seconds, you'll get the energy in joules. And we'll do that as an example just because it's fun. Yeah, that is a good one. Okay, one last pretty cool thing, and it has to do with capacitors. Now, they give you these equations for charging and discharging capacitors, but I want you to understand them conceptually. So imagine that I have, let's start with the first case, a capacitor, and it has charges on it. And then I connect that to a resistor, which could be a light bulb. So R. And this is capacitance C. So if there's a charge on this, and there is a delta V. So I could say delta V, let's just call it VC, voltage across the capacitor, minus IR equals 0. That's just the loop rule, right? If I go this way, the current's going to be like that. If I go around the loop this way, I get that. You can actually do it by looking at the electric field inside of here too, but let's just think of it this way. But if there is a current, then what's going to happen to the charge in the capacitor? If there is a current, this charge has to decrease, because where's the current coming from? These positives are coming around here, getting up over there, and so you end up with a lower charge. If you have a lower charge, this is going to get smaller. If the voltage across the capacitor gets smaller, the current gets smaller, which means that it loses charge not as fast. So overall, this will not power this light bulb forever. It will slowly dim out. So let's see if we can make this happen. I'm going to start off. I have a capacitor right here. It's a parallel plate capacitor. Doesn't look like it, but trust me, it is. I'm going to take this. Let's see if we can just charge it up, and then we'll use it in another way. Connect that. Come on. I guess I should just use the clip wires. Okay, let's use some clip wires because it'll be easier. Okay, so I'm going to take this wire and clip it to this side. And then I'm going to take and clip it right there. And then I'm going to take this side. And I don't want the wires to touch. Yeah, this is easier. And I'm going to clip it right here. Now, you can't see anything happening. But what is happening is that current is flowing onto the capacitor until the voltage across the capacitor is equal to the voltage of the batteries, and then current is no longer flowing. And that's called charge up. And this will happen fairly fast. So now I can disconnect this, and let's connect it to a light bulb. So I'm going to just take this, connect it right there, take this. I don't need the battery anymore. And I'm just going to, connect this right there. And now I'm going to just connect this, and nothing happened. Look at that. Nothing happened. What the heck? Why did nothing happen? Do I have a broken bulb? No. Okay, well now I'm charging it with the light bulb in there, which is fine. I'm going to let it decrease all the way. I guess I didn't charge it all the way. You'll notice that it is dimming down, and we'll look at that in a second. Now I'm going to, the battery's not there. I'm going to just touch it right here, and it's not working. Why is that not working? It charged. Okay, well, I'm not going to waste my time. So it would charge up, and then it could discharge through the through the light bulb. And if you looked at current as a function of time, it would look like this, an exponential decay. The other case that we can look at is charging a capacitor. So suppose I put a capacitor in with a resistor, and this is plus, so I'm going to have a current going that way. I'm going to get positive charges built up right here. But you'll notice that the orientation of the charge on the battery and the capacitor are opposite because of the way the current flows. So eventually this will be some EMF, and this will be negative EMF, in which case then the current will now be zero, it'll be charged up, and it'll stop. So you'll get the same looking current, but it'll be in a different direction. Okay, there was something else about capacitors and charging capacitors I was going to talk about, and now I can't remember what it was. Two things about capacitors in a circuit like this. In a DC circuit, capacitors, at t equals 0, they act like a short. So right when I plug this in, if there's no charge in the capacitor, there's no voltage across it. So it acts like it's not even there. And that's what we call a short. At t going to infinity, they act like an open. So an open circuit would be a wire that's just taken apart. And so if, as time goes on, this acts like it's an open circuit and it stops the current. And those are the two most important things. I'm not going to have you do the equations for exponential decay. It's not impossible, and it's kind of fun, but there's just a lot more stuff to do with it. Let's see. No, we did that one. Okay, good. So like I said, that was quite a bit for Chapter 18. Most important thing, what is electric current? Why do we have electric currents? And then how we deal with simple circuits. Power is one that's going to be big for me, and that's that.